All right, welcome back everyone. In this section, we're going to go through example 5.5 and a lot more. You ready? Let's do this. In this video, we're going to go over keratometry, lens clock. We're also going to talk about fundus lenses, and then we're going to wrap up with ANSI standards. All right, so let's dive into the text. The first thing we want to talk about is a keratometer. So we're going to be talking mainly here about a manual keratometer. I know in clinic, guys, we all use an auto keratometer, right? Or we use an auto topography to tell a lot of the information we need to know. But optics-wise, we want to go over and kind of brush on the manual keratometer, so at least to kind of have an idea of what's going on here in case a question comes up, right? All right, so the first thing we need to look at is, what does a manual keratometer do? Right? Well, what does keratometry in general do? Well, it gives us the radius of curvature for what? The center part of the cornea. That's exactly right. Good job, guys. So highlight that in the text, right? So measures the radius of curvature right below that center of the cornea along certain axes. So that's awesome. So what I want to do is I want to go to the whiteboard now, and I want to draw a picture to kind of help illustrate this point. So whenever you think about looking at a manual keratometer, right, what you're actually viewing whenever you look in the ocular there, this is kind of representation of what you're seeing, right? You kind of see three circles, right? And then you see a circle down here on the right that has two lines to it that cross, right? And you have two circles that just have one line that crosses, right? And so the whole concept with manual keratometry, right, is that how a manual keratometer measures the curvature of the cornea is that it thinks of the cornea as a mirror. And what you do is you actually reflect these mires, are what they're called, but these circles with the lines in them, you actually project those onto the cornea, and then you get a reflected image. And what you do with the dials whenever you move those, right, is that you're actually measuring the size of the reflected image, right? So my question to you is, we've got three circles to look at. So here's circle one, right? Circle one here, circle two, right? And circle three. Okay, so whenever we're looking at that, which of those three is going to be the reflected image off the cornea? Yeah, it's exactly right. It's going to be number two, right? So here's the reflected image. Right? So there's a reflected image off the cornea. So what you're doing is you're actually, whenever you're moving the dials, you're actually moving this circle in and out so that these two crosses, right, overlap. Right? And the same thing's here. Whenever you're moving your horizontal dial, right, what you're doing is you're measuring the horizontal size of this reflected image, and you're moving your cross in and out so that they actually overlap each other. Whenever they overlap each other, horizontally and vertically, right, then what you're going to do is you're actually measuring the size of that reflected image. Okay? And that's going to be in the text. You guys will see that there on how it works, right? Right there listed for you in text. The key thing to circle there is, remember that it thinks of the cornea as a convex mirror, right? And what you do is the second line, you measure the size of the reflected image. Very good. Now, whenever you measure the radius of curvature off of the cornea, usually, right, the manual keratometer and especially your automated keratometers, right, will give you a value that's actually going to be a diopter value, right, or a DK value, right? And what does that mean? That means diopters of the cornea. Okay, so what happens is that the machine measures the radius of curvature of the cornea, and then it uses F equals N2 minus N1 over R, right? Remember the lens maker or power equation, right? And you'll see this in the box right here in your text, right? And what it does is it uses an assumed index of the cornea, right? So the assumed index of the cornea, so the index of the cornea, right, is going to be equal to 1.3375. Right? So what happens is that the manual keratometer or your automatic keratometer, right, it automatically does this calculation for you. It measures the radius, and then it plugs in 1.3375 for N2, subtracts that from air, and then it plugs out for you a diopter value. So whenever you see a 42 diopter cornea, 44 diopter cornea, what you need to think is that that is a diopter value using the index of the cornea to be able to calculate that. And that's right there in the text. All right, guys, let's clear the whiteboard and continue talking about ophthalmic instruments. We're going to go into lens clock next. All right, so let's talk about a lens clock. All right, so next thing we're going to talk about is going to be a lens clock. And what's a lens clock used for? Right? That's exactly right. It's used to measure sag. Right? So a lens clock is used to measure the sag of a lens. And you guys want to highlight that there on the first line in your text, right? So you want to highlight that measures the sag of a lens. All right, now how does it do that? Well, if you think about it, you've got a lens here, right? And you're going to have three adjustable prongs, right? 2 of them are going to be on the outside, right? Sorry, 3 prongs, only one of them is adjustable. You got 2 prongs on the outside that did not move, right? And you got 1 prong in the middle, that's the adjustable one, right? So this one you adjust, right? And so this middle one will move in and out, right? For you to be able to measure the sag, right, of a lens. So whenever you think about your lens clock, that's what you're going to use it for. Now, some of you guys are like, Ryan, I don't remember the lens clock very well and I haven't seen it in a long time. Well, just next time you're in clinic, go to your optical. They're going to have a lens clock somewhere. They're probably going to have to dust it off a little bit, but they're going to have a lens clock somewhere. That way you can look at that and kind of get an idea of what's going on with your lens clock, right? So what happens is that because that middle prong will move in and out, right? It measures a sag of a lens. It'll give us a dioptric value, if you remember, right? The lens clock doesn't give us a linear value for the sag, which we know it would be, right? It actually spits out a dioptric value, right? If you look at your lens clock. So how does it do that? Well, it's a good question. Well, what it does is, once again, it uses the same equation we talked about before, right? N2 minus N1 over R, right? And what it does is it converts the sag into radius, and we'll talk about that equation in just a little while, right? In the next video talking about thickness, but it automatically converts your sag into your radius, and then what it does is it has a calibrated index for your lens clock, right? So every lens clock is calibrated for a certain index value, and because of that, it's automatically calibrated to spit out to you the dioptric value. So whenever you do lens clock, you get a sag value, right? But it doesn't actually give you a distance, it gives you a dioptric value, okay? And if you look in your text on how it works, all that information is right there for you, right? And what you want to highlight is the second sentence, right? It says, based on the sag value and an assumed index in the value used for calibration, right? Lens clocks give you a power readout, right? Okay, so now what's the natural question that would come from that is, okay, or how do you stretch this concept, right? Well, naturally what you would do is say, okay, well, let's use the lens clock on a lens that has a different index than what it's calibrated for, right? And so how are you guys going to attack that problem? That's exactly what equation 5.7 is for, right? So how you get the power of your lens, right, with a different index than what the lens clock is calibrated for, is you take the index of your lens minus 1 over the index that the lens clock is calibrated for, minus 1, and you multiply that times the power the lens clock gives you, right? So whenever you do that, that'll allow you to be able to adjust for the index that you have in your lens in the problem. So let's clear the whiteboard and go through example 5.5. You use a lens clock calibrated for an index of 1.5. You want to measure the power of the lens made from a material of 1.7. The power readout of the lens clock is plus 6. What is the actual power of the lens? Take a second. Pause the video, work that out, and then we'll come back together and work it again. So when we look at the solution for example 5.5, right, it's a simple kind of calculation where all you got to do, the main point here you got to do is just remember the equation, right? So remember the equation, everything else is good, right? So we plug 1.7 as the lens, the index of the lens that you are measuring the sag of, right? And then you got the lens clock is calibrated for 1.5. Lens clock is giving you a 6 base curve, right? For 6 diopter base curve for the pair of glasses, and you want to know what the actual base curve is. You plug all that in and you're going to get 8.4 as your answer. So the key point on this equation is pretty simple as you're going forward. It's just going to be one of the ones you need to kind of remember, just kind of highlight that, put it on your equation sheets, that way you have that to be able to use it moving forward. So remember, the key point with lens clock is that it measures sag, right? But it actually gives you a diopter value for the base curve, right, on the readout. So you're going to have to be able to remember whenever you've got a lens that has a different index than the index of the lens clock, how to convert, right? So once you get that down, you're going to dominate these kind of questions. Excellent. Let's keep on going. We'll clear the whiteboard and keep on moving on to our next topic. So now what we're going to talk about is fundus lenses, right? We're all used to using fundus lenses in clinic, so just a couple of points optically that we want to bring out about fundus lenses. And whenever I'm thinking about fundus lenses here, I would probably think about your standard 60, 78, 90 diopter lens. I really wouldn't worry too much about your superfields and superpupils and things like that. So the key point that I want you guys to remember, it's boxed right here in your text for you, is that higher powered fundus lenses give you lower magnification and increased field of view. So you want to put a highlighter box around that, star that, really important. Now the next thing I want to go over is talk just a little bit about the different aspects of the magnification of the different types of lenses, and it's particularly we want to talk about the 60 diopter lens, right? Because what's one key point to remember about the 60 diopter lens is that it gives you a magnification, right? Your 60 diopter lens, right? gives you a magnification of -1x, right? And so that's a key point. So let's talk about how that comes into play, right? Now we've talked a little bit about telescopes so far, and we're going to get more into telescopes whenever we get into low vision as well. But whenever you think about a fundus lens and an eye, right? So we put our eye up here, right? And we put our fundus lens in front of the patient, right? What's going to happen is we're actually going to create a telescope system, right? With an objective, right? And an ocular, okay? Whenever you look at the actual optical setup. And this is right here in your text on why does a higher powered fundus lens result in less magnification. All right, so whenever you look at this, we see that you end up developing a telescope system. And so what you get is we're going to talk about this more, but magnification, right, for a telescope is going to be equal to negative power of the ocular, right, over the power of the objective, right? So over the power of the objective. And we're going to hammer this pretty hard whenever we get into low vision. So don't worry about that too much right now, but I just want to kind of plant the seed as to why you get this aspect of a 60 diopter lens having a 1x magnification, which is a key point. All right? So whenever you break this down into the fundus lens and your eye, what ends up happening is you end up creating this kind of a concept of a kind of a reverse telescope, right? Because we've got a plus 60 diopter lens here, right? And you think of the eye as being a high plus powered lens, right? We essentially create a Keplerian type of telescope, right? And so what that breaks down to is magnification equals negative the power of the eye, right? Because that essentially becomes your ocular over the power of our fundus lens, right? And that essentially becomes your objective, right? So we get pretty much a Keplerian type telescope. Well, we're going to also talk about this later on whenever we get to physiological optics too, right? But with the reduced eye model, if you guys remember, what's the reduced eye model standard power for the eye? Yeah, that's exactly right. You guys are dominating this, and that's something we're going to talk about later on, right? That's going to be 60 diopters, right? So if you look at the reduced eye, the standard power for an emmetropic eye, that's going to be plus 60 diopters, right? Well, if we plug in our fundus lens, right, then we're going to plug in plus 60 diopters here as well for our fundus lens, and that's how we get a -1, right, magnification with a 60 diopter lens, right? So what that means, right, is that you get that whenever you measure the optic nerve with a 60 diopter lens, right, and you look at your slit lamp, right, and you look at the actual height of your slit lamp beam, that'll tell you the exact height of the optic nerve, right? Now, what you guys also need to remember is that whenever we're doing fundus lenses, right, we're also having a slit lamp here, right? So we have a slit lamp that we're looking through, right, and that's going to create magnification. So the overall system, right, of you looking at the patient, you're going to get magnification because the slit lamp is going to create magnification, right? But if you look at the light coming from your slit lamp going into the eye, right, that light going into the eye is going to come back out of the eye the same height, right? So the light that comes into your eye is going to come back out of the eye the exact same height, and that goes back to this magnification of 1x, all right? So hopefully that made some sense. If you guys look in your text, there's some things here I want you guys to highlight as we're going forward. If you look at that and go, Ryan, that seems a little bit complicated to me, I don't know if I get that. The key point to remember is that a 60 diopter lens gives you -1x, right? So if there's one thing you're going to say, Ryan, what's the basics of what I need to know? That is it, and that's what you want to highlight in your text. So if you look in your text, you'll see that if a 60 diopter lens, and you'll see it equals -1x, and that's what you want to circle, highlight that, right? Now, if you go on in your text, you'll see that a 78 diopter lens, if you put in 60 here and you erase this, right? And now we put in a 78 diopter lens, right? Whenever you do the math on that, you get -0.77, right? So you get -0.77x, right? And so that's why a 78 diopter lens gives you a less magnification. Now, once again, and in the box right here, it reminds you is that your slit lamp is going to give you magnification overall. So whenever you answer a boards question or a test question or a smart test question, it asks you and says, you get a higher powered fundus lens, what happens to magnification? And you say magnification gets less because it does, right? You need to also separate out in your mind that clinically, whenever you put a 78 diopter lens up in front of the patient, you're going to see overall magnification in what you're viewing, right? Because you have the slit lamp and that has magnification. That's right here in the text. So remember that a slit lamp itself creates magnification as well. So you want to highlight that and star that, right? And then lastly, you have a 90 diopter lens, right? And the magnification that a 90 diopter lens is going to create is going to be negative 0.67 times, okay? Now, I get asked this all the time. Ryan, do I need to know the 0.77x and the 0.67x? And I'd probably say that that's not incredibly high yield information to know. I think the key picture whenever you step back and think, okay, what is the key picture with fundus lenses? It's this. Whenever you increase your fundus lens power, so you go from a 60 diopter lens to a 78 diopter lens, right? What happens? You get lower magnification and increased field of view, all right? And then the other key piece of information you need to know is that a 60 diopter lens, there we go, that a 60 diopter lens creates a minus 1x magnification, okay? So it doesn't magnify, it doesn't minify, and so you can actually directly measure the height of the optic nerve using a 60 diopter lens. All right, guys, that's kind of that's good information for us to know. I think it asked a lot in terms of like the why behind this concept, and so that's why I want to take a little time to go through this. Hopefully that made some sense for you guys. Let's finish this section strong, talking about everybody's favorite topic, ANSI standards, right? So I know whenever we lecture on ANSI standards, everybody kind of rolls their eyes at me, and you're probably rolling your eyes at me right now on your camera, right? I can see it all the way here. But you know, certainly I think it is still something that's important to go over. So let's just kind of hit the high points here and then we'll finish up our section. So if you guys look at ANSI standards, there's 3 boxes here in the text. You'll see there's ANSI standards for sphere lenses, cylinder lenses, and then kind of miscellaneous box. So 3 boxes there of ANSI standards. For those of you guys that look at that and think, oh, Ryan, I don't want to memorize this, I would say, okay, then skip that and focus on something else. It's not like it's a huge point, you know, moving forward for boards. But you know, on the flip side of that, it doesn't take a lot of brain power to memorize these 3 boxes in case it comes up on a question. So that's why I highlight that. The 3 boxes are there for you. So I give you some option in terms of on that part. Now, if you guys look on in the text, you'll see the Z87.1 safety standards, right? And these, I think, are higher yield and really important. So you'll see that box. You want to put a highlighter box around that, right? And that's the drop ball test and the high velocity impact test, right? So you'll see both of those there for you. You want to highlight around that. I do think that is some good information. There's only 2 of them there to know. So even those of you guys like myself that aren't very good at memorizing things, we're more of like understanders, right? You can at least memorize 2 things for Z87.1. All right, guys, go dominate the quiz, and I'll see you on the next section.